Hey folks, happy Thursday. Hope you're doing well. Sorry I missed you on Tuesday. I was out. I thought it was fine too, which was really funny. I had my morning class at 10, and I was like, yeah, I'm feeling okay. And then right about 24 hours after I got that second dose, it just hit me, and I was out cold. I slept like all afternoon long, most of the night. It was pretty crazy, but glad to be back. Sorry for the delay. Hopefully you saw I did move the due date for this Polynomial, that's the name of the project, Polynomial Project, out. I was getting lots of questions about it and wanted to be able to chat on Tuesday about it. It didn't happen, so I pushed that out a little bit. I want to make sure we've got some time to answer those questions about the Polynomial Project. And then we're also going to start talking about the final project as well, which should be really exciting. I think that should be a lot of fun. Should be a lot of fun. We'll see. Not everyone always thinks it's necessarily quite as fun, but we can go from there. And then hopefully we'll have a little bit of time to talk about binary search trees. If we need to push that back a little bit, that's okay. You know, as we get to this tail end of the semester here, we've got a little bit of wiggle time if we need it. Sorry, I've got these scabs that are super itchy. They drive me nuts. So let's see. So yeah, ideally binary search trees was on tap for this week. Or any search trees, usually they're binary search trees. Sorting and selection, some final project work time. So we've got some time set aside for us to do this. And then as we start talking about the final project, if you can set this time aside, 6 p.m. to present synchronously, we'll probably do like a Zoom call and everyone can take turns sharing their screen or pairs. You're welcome to partner up with a classmate for this one and present your final project. It should be a lot of fun. We're doing this in lieu of the final exam, so I think this time slot should be open for everybody. I know one person had a conflict, so if you absolutely can't make it, you know, we can work around it. You can record a presentation or meet with me at another time, and we can go from there for it. But we are in the tail end. We're week 12 now, so which is like, what, 4/5 of the way done. It's kind of amazing. We'll finish this up and move into the rest of what we're going to do in April. It's pretty exciting to get close to finishing this up here. So hopefully it's been going well. I know, so still haven't gotten a lot of those grades in. I apologize for that. I'll be working on that. It's apparently I can't catch a break, so I'll be working hard on that to get caught back up. So the project here, Polynomial Project, had lots of questions about that one. So let me fire up PyCharm here. See if we can get some ideas kind of just sketched out on how this might work with polynomials, right? This idea that they're linked objects and how they interact with each other. Sorry, scab is annoying. Ouch. And let's get like itchier when you pick at them. It's the worst. Absolutely worst. All right, PyCharm, come on. Working here. Even loading anything? Ooh, yeah. Shouldn't have picked it that one. Ouch. Come on. Oh, we also had the lab on Monday as well. I don't think anyone actually started it yet, though, so that's okay. We can work more on that later too. So let's start up a new project. Come on. Okay, while that loads, let me fire up the whiteboard here. And we're going to kind of walk through some of these steps, step by step here. Clear that off. All right. So remember, when you have a polynomial, let's just pretend we have a large one. Again, there's no way to get a large one without adding much together, but okay, we'll go through all the steps. So let's make some polynomial. Let's say like 3x to the 4th. That's a polynomial. If we want to add another polynomial there, let's say maybe like 2x to the 3rd. What are we going to do? Now, this one doesn't change, and this one doesn't change, right? Math doesn't change your original, what do they call those? The operands, right? We're not changing the things we're operating on. We are creating a new result down here. So what do we need to do? If we want to keep this in the correct order, right? Well, we need to find out which one has the bigger exponent, or maybe they have the same exponent, right? We need to find bigger or same, right? Or really just start with the bigger one. And it shouldn't matter too much. You know, lots of different ways of approaching it. That's fine. So which one of those has the bigger exponent? Right? We have this one is self right now, right? So this is self, and self has the what did I call it? I think it was the first term or the head. No, I think I had a name for it here in the description. Go find that assignment here and add that one in. Come on, friend. There we go. Edit. That was not it. More options. That's the edit I want. Come on, Canvas. Yes, your polynomial, oh, the first node, right? So we would have a first node. So this is self first node. Okay, and this one over here is the other first node. Right, so I can say, hey, is my self first node bigger or is the other first node bigger? And by bigger, I mean which one has the larger exponent. So which one of these has the larger exponent? Well, fourth. 3 to the fourth, okay? So that will be the first term in my new polynomial. Right, we'll get 3x to the fourth. Great. Well, now that I've added this one, now I need to be looking at the current term. Remember when we take linked lists, we kind of do this walking process where we start with one, we move to the next, we move to the next, we move to the next. So then my, self current should become the first node's next. Does this one have a next? No. So my self current is going to be none. That's okay. It's all right. This, other current starts off as this one. So this is other current. Okay. Now I can say, hey, which one has a bigger exponent? Oh, well, I don't have one at all, so it's got to be this next one here. So then I'll add in there 2x to the third, and then other current goes to other currents next. Does it have a next? No. So other current becomes none. And I say, oh, they're both none, I must be done. I've gone through all the terms. Now I have a new polynomial result, right? New polynomial takes the init method, the constructor here, should take an exponent and a coefficient, or coefficient and exponent. I don't care, whichever order you want, just as long as you make sense of it. Probably makes sense to make the coefficient first, because it's usually how we think of them, but it doesn't matter. It's all fine. Okay? So we'll make the first one. And then to set the next one, well, now we have a new current, which starts off as the first node. Right? First node has a next property. To add a new term, we have to make a new term and set it as this one's next. Becomes that new term. And then current needs to move to the next. Now current now points at the next. That way I can add another term if I need to. Because I always need to be able to add new terms and add new terms and add new terms and add new terms. Right? Okay, so we got 3x to the fourth plus 2x to the third. So let's take that polynomial. 3x to the fourth plus 2x to the third is one polynomial here, right? This is the first term. First term has a next. The next term is none, right? Its next is none. That's okay. That's all right. That means it's done. Now let's add another polynomial to it. Let's add, say, I don't know, 2x to the fifth. Okay, if we add these two together, right, we start with the self first, the other first. And we see which one's bigger, which one has a bigger exponent. So my new, well, the ones with bigger exponents, 2x to the fifth, 2x to the fifth. Great. Now other current needs to move to the next. Its next is none. So other current becomes none. That's okay. My self current becomes the head, right? Self current, or becomes the first node. Great. Well, which one's bigger, a none or something? Well, it must be the something. So then I'm going to add 3x to the fourth. Self current goes to the next. Next is this one now. Sure. Okay, let's add 2x to the third. Okay, self-current goes to next. Now next is none. Okay, we're done. Here's our new polynomial result. Cool, no big deal. You with me so far? How's this feeling? Is this helpful? This idea we have to keep all of these pointers going, right? So to add another value, again, right, we had new polynomial was this one. Its first term was the current. To create a new polynomial, we need to set its next equal to a new term, given these values. And we need to make sure we're using copies, right? If we just use references, we say, hey, if your term equals this term right here, I've got a shallow copy. And if anything ever happens to this one here, then it's broken, right? And if I go change this next value to be something that's not this one, now I've broken my original. So we can't use references. You have to use copies, right? And it's not hard, right? Term takes a coefficient and an exponent. So just hand it the coefficient and the exponent. It will make a new term in memory. You've got to be using new terms. Super important here. Right? You could use the deep copy library, but I mean, it's just a one-liner to take the current terms coefficient and current terms exponent and hand it to term to create a new one. Not a big deal. Either way is okay. And after we add one, then current term needs to be pointed now to current terms next. That way, next starts off as none, but if you want to add a new term, you can add it, and instead of being none, it will become this new term. You make a new term, you make a new term, you make a new term. Right, so we have three different pointers going on. We have the self-current, we have the other current, and we have the new current. And I have to keep track of all three of those to see, okay, is this one going to go in, or this one going to go in, or this one going to go in? Now let's do another one. So let's do, if we have 2x to the 5th plus 3x to the 4th plus 2x to the 3rd, and let's add in, say, I don't know, 7x to the 4th. Okay, let's add those together. Okay, so I have the first term of self. I have the other first term. Which one has a bigger exponent? Right, well, self. Okay, so we get 2x to the 5th. Now I have a new polynomial. Okay, new polynomial. Great. Now I took the one from self, so my self current needs to be this one. Other current is this one here, so then I have other current. Great. And now I have the new current. Starts here. Right, so we've done the first term, so now which one is next? Well, they have the same exponent. We haven't done that one yet. So if we have the same exponent, we just add the coefficients. So then we'll get in here, we'll add in, we'll say, okay, my new current's next is a new term of 10x to the 4th. Just add those coefficients together. Now both move, so self-current moves and other current moves. Other current's none, sure, we're done with the other, and we're going to take the self, plus 2x to the 3rd. So new current now points to this one, and new current's next equals this one, and then new current moves. Right, so this idea that we keep on having to use those pointers of where we are, and we can add next, and add next, and add next, or move to the next one, and move to the next one, and we just keep track of where we are in all of these. Right, and the whole thing pans out. So pretend we had this like huge polynomial, right? So we had like 3x to the 11th plus 4x to the 9th plus 21x to the 5th plus 2x to the 4th plus 3x to the 3rd plus 21x. Sure. Well, that's to the 1, right? To the 1. And then let's add another polynomial. Let's have like, I don't know, 9x to the 10th plus 11x to the 9th plus 7x to the 8th plus 5x to the 4th plus 2x to the 3rd plus 5x squared. Sure, something like that. We have two really big polynomials. I don't know why that didn't finish writing, but that's fine. Right, the whole process still works. Right, we look at the firsts. Look at the firsts. We create a new one with the largest exponent, so 3x to the 11th. Now I have my self-current, and I have the other current. Right, other current stays here. I took the first one, so self-current starts over here then. Right, and you can kind of imagine you cross them off. We're not actually changing anything. Hey, math friends. Prof. Peter, thanks so much for coming on by with your class. Welcome on in. We're talking about polynomials. Not super high-level mathematics here, but we're having some fun with them. And we're seeing how we can store them ourselves using a singly linked object. It's a lot of fun. It's a lot of fun. And, you can catch me if my math is wrong. We take our largest exponent. And now we're going to look at, hey, is self-current bigger or is other current bigger? Which one has a bigger exponent? And now I have a new current as well. New current. So that's the new current starts here. If I have one to add, I'm going to take the bigger exponent. Okay, sure, let's take 9x to the 10th. So new current's next becomes, right, that's a next really, 9x to the 10. Great, that one's done. Now other current points here. Okay? Which one is bigger? Well, they're the same. Okay, let's add our coefficients together. So now new current next is this one. New current is this one. Right? New current's next. Let's add a new one. Here becomes 15x to the 9th. They both move. Other current moves here. Self-current moves here. Which one has a bigger exponent? All right, well, we're going to take other current. So we're going to say, okay, new current's next had to move. Sorry, we always move that one. Its next now is 7x to the 8th. That one moves here. Now new current moves here. Which one is bigger? I've got a 4th and a 5th. Okay, let's take the 5th. So now its next becomes 21x to the 5th. All right, this one, self-current, moves to here now. Which one is bigger? Well, they're the same. Let's add our coefficients. So new current moves here. New current next becomes a new 7x to the 4th, and on and on and on and on. Pretty five-head. I don't actually know what that means. I'm a little dumb, I guess. Okay, but the idea is we're not changing the original. We're not changing self. We're not changing other. We're creating a new result and using this new current pointer to change the next every time. We'll say its next is equal to a new term. And we hand it the coefficient and the exponent. Big brain. Oh, you make the 4-head turn into a 5-head. It increases the size of your brain. Polynomials are fun. Now, we're going to do a bad thing here in a second, so don't judge me. But, we're trying to keep things relatively simple. If I were to take one of these big polynomials and I wanted to differentiate it, right? So we had, say, 9x to the 10th. These numbers are going to be really big for me to do this math with, but that's okay. 15x to the 9th, 7x to the 8th, 21x to the 5th, 7x to the 4th, on and on and on. If we wanted to differentiate this, right? I'm not going to change the original, right? I'm going to say, oh, that's a 10 there, right? 10. I'm going to make a new polynomial. What's the first term going to be here? Well, I take myself. I have a current node, right? Current starts at my first node. What am I going to plug in here for my new term? Right? Remember, I don't want to change my original. I want to make a new term. Well, we need to do that math, right? We take the exponent down by 1 and multiply. Right? Is that 90x to the 9th? Hey, thanks so much, Nandari. You take care. Right? And then our current now moves to the next term. And now my new current is here. We're going to set its next to this next number. So what's 19 times 15? That's 90 plus 45 is 135. 135x to the 8th. That sounds about right. And then new current moves to this one because we set new currents next. And then we can set new currents next to the next one. So self current moves to the next one. Plus 56x to the 7th. Right? New current next becomes new current. Self current next becomes self current. Right? 105 x to the 4th. Right? New current moves to this one. We added the next. Self current moves to this one. 28 x to the 3rd. Right? New current moves to this one. Self current moves to this one. We're at none. We're done. Right? We have a new polynomial result to return. Okay? Let's reverse it here. So if we had 90 x to the 9th plus 135 x to the 8th plus 56 x to the 7th plus 105 x to the 4th plus 28 x to the 3rd, and we wanted to integrate. Again, we're kind of cheating here with our integration, right? Don't worry, it's okay. We're just going to assume there's a constant 0 because we don't actually care. We're just pretending here. We're not in real math land. All right, so we reverse our operation. So we add 1 to the exponent, and then we divide by it, right? So our new poly, right, starts with our current. This is our self-current. And our new poly, right, we don't have one yet. Well, we need to do the arithmetic. So we add 1 to the exponent. So our exponent's 10, and 90 divided by 10 should be 9. So 9x to the 10th, right? I guess my 10 should be a little smaller there. 9x to the 10th becomes my new poly, my new polynomial. Now I have a new current. That's the current node. I can create its next. So my self current goes to the next. I will set the next term of the new current, to be, what did that used to be here? Because I can't do the math in my head. So add the exponent, it goes up by 1 to 9. We have 135 divided by 9 should be 15. That sounds right. Is that right? Probably is. Probably close enough. Okay. And we add that term. Then new current moves to new currents next. Self current moves to self currents next. Right? We just keep on walking it through. Does that part make sense for how we're going to just follow this trail? We're just always going to keep looking for next and looking for next and looking for next. Kind of like a loop, like while current is not none. Right? That says is not none. That's okay. That's official Python right there. Handwritten Python. That's like artisanal Python. Right? You draw the stuff by hand. Okay? Does this sort of help with some of those operations? Remember, if we always add them in descending order, we take the largest exponent first, we're already there. We're already in sorted order. We don't have to manage any of that. All we need to do is just make sure we add them together properly. Because we only ever start with a single term, right? So as we start adding terms, we start turning into real polynomials instead of monomials, right? We just make sure we add them in descending order and we're all set. We never have to do any real sorting like that because we know they're sorted. So you can assume all of your objects are sorted because you made sure they are. Okay, and we don't have to do anything fancy like trying to no differentiating a constant, right? You could differentiate 3x, right? We could do that, but we can't differentiate 3. We're not going to, right? We're not going to differentiate 3. Okay, just don't bother. It's okay. All right, and same with the integrations. Like they get funny with was it -1s or something? Don't bother. It's okay. We'll just pretend that hard stuff doesn't happen. It's okay. This is like business calculus, right? They never have any of the transcendental functions. Is that the right term? I think that's the right term. You know, funny enough, my calculus textbook, which I recently, well, yeah, it is still recently, a couple years ago now, took calculus. I never needed it for my undergrad. And so when I wanted to get into the doctoral program, they said, oh, you need calculus as a prereq. I said, oh, okay, well, I'll go back to school. I'm 30. I can do that. It's a lot harder to memorize stuff at age 30 than it was as a teenager, turns out. That's okay. So my calculus textbook that I got is currently my monitor stand because I have my laptop here and I have a second monitor above it. And the second monitor just needed like an extra 2 inches tall. And I was like, oh, hey, I got a book and it fits underneath the you know, because the stand of the monitor is kind of large. Like I can put this book down here. So that's where my calculus book is. Someday I'll get it out and I can teach my son some calculus, but he's still working his way through trigonometry and other things, but he was excited to learn it because I told him how cool calculus was. It's actually really fun to take as an adult and like kind of appreciate some of the cool things you can do with calculus. And then in terms of like computer science and data science, when you get to Calc 2 and series and sequences, it's just amazing. Like that sort of stuff is super cool. So big shout out there for math. And I forgot to give you a shout out, my friend. Let's see if I can spell your name right, or maybe I can copy paste it here. Where's my copy paste option? Nope. Oh, come on. That's all right. I'll just try and spell it. Your name's not so hard. I think I did it right. Does that link work? The link probably works. If I open that up, you're probably like, what, hosting my channel now or something? Let's see. Did the link work? See if we can get some Twitch inception. I think it worked. Professor's a hard word to spell. It's got like double letters and everything in there. English is hard, friends. Let's see. Can we get some Twitch inception? Nope, nothing. My computer's been sad lately. I think it just messes with the processor because it knocks it down a notch. It makes it run really slow if it's too hot. I gotta try and clear out the cat dander or something. Yeah, there we go. I found your channel. I did it right. I won't even let it load. It screws up. All right, folks. You feeling good about this project then? We all right so far? Polynomials with linked objects. Again, we could store these other ways. We know there's other ways to store them. But storing them with like array-based storage, every time we need to resize our storage array is going to be slow, right? Versus just adding a new link to the chain is really easy. Because it's kind of hard, like even if we have like two 50-term polynomials, it's a little bit hard to judge how many of them are going to combine because they have like exponents. So I can't say, oh, let's make a new array of size 100 because that's the most I need. And we could, but it'd be memory inefficient at that point because we're storing more spaces than we need for all these terms. So we got lots of options, but this is kind of a fun way to go about it here in a nice object-oriented approach. Okay, so that covers the addition of multiplication. I'm assuming you can do if we can add, differentiate, integrate, turn it into a string, deal with it here. When we toString, like round your coefficients to 2 decimal places, make that look pretty here in case we do a bunch of division. Those can get really big. Equals and not equals, right? Should be comparing, do your terms have equivalent values? So this equals and not equals in term, we want to override. We don't want to say, hey, are you the same term? Are you the same location in memory? Because a 3x to the 7th should be equal to another 3x to the 7th. So we need to define that here. And the same idea with polynomial, right? I don't want, are you the same polynomial in memory? I want, do you have equivalent terms? So we need to go through every term and check, does your term match this term? Does your term match this term? Does your term match this term? If they all match, great, we're equivalent, we're equal. If we find one that doesn't matches, we're done. They're not equal. Okay? And then we're going to add unit tests to make sure we get our code coverage. Right? Make sure anytime we have an if or an else, we're testing out the code there. So this is just some examples of what this output might look like. Okay? Feeling okay so far? And I think, did I put a rubric out there for this one? I thought I did. I don't see it in this view though, do I? Pretty sure I put the rubric out there. Let me hit cancel on that. So let's do Tuesday, April 6th, right? Tuesday. I know what day it is. Monday's lab day. Yeah, so Tuesday I'll go over the solution to this. Yep, and here's our rubric, right? So the term node class, 3 points, 3 points for add, 3 points for multiply, 3 points for differentiate, 3 points for integrate, 3 points for string, 2 points for equals and not equals. Right? The term node class was including its equals and not equals. Like that's just all one thing for term node, right? Having all of those in there. Okay. There's points in here. So having the function and then the unit tests are points. So it's a half and half. So I didn't want to like double all these up because then it's a bunch of extra things to click on. So you get a 1.5 for doing integrate and a 1.5 for unit testing integrate, making sure you did it right. Okay. So there are points for the unit testing. They're just not called out separately here because I didn't want to have a bunch of different items. Is that okay? Hopefully that's not too confusing. Okay, cool. All right, you've been quiet, class. Hopefully that's a good sign that things make a lot of sense. We'll see. We'll see how that goes. You with me? Let me throw a poll out here for fun. Let's see. No notes. Got it. So, a couple questions here for how you feel about the Polynomial Project. You got it, you're unsure, or you're going to fail it. Let me know what you think there in Twitch chat. Go ahead and put that in there for me. Okay. Awesome. Yeah, write some more unit tests. That's great, Sammy. Good to hear. Yeah, the equals and not equals. Again, it's a similar idea, right? How do I compare myself to the other? And we're going to just walk through every term using current term, moving to current terms next, current terms next, current terms next, with mine and other. And they just kind of walk in lockstep, seeing if they're equal or not. Okay. So let me know how you feel. Unsure is okay. We got a little more time to work on it. We got lab time on Monday. Should be okay. I have to be out in Troy to get my daughter her COVID shot on Monday. It's at like 12:30, so I should be back in time for lab. If you're running the questions, we can definitely use that lab time to talk about the project as well. So let me know how you feel about that. Okay. Hopefully it's going well. This was our last individual project, and then we can go from there. All right, awesome. So before we jump into binary search trees, maybe I'll save some of that for a little bit later. We should talk about the final project. We can get started on that. Again, ideally this project was done today. I know we had a little bit of moving stuff around, so I'm not too concerned if that's late. But I want to let you get started on the final project. Excuse me. Let me put the final project out here. And this one is 30% of your overall grade in the class. Imported assignments. That shouldn't even be a group. I delete that. There we go. Delete. Okay. So there's no final exam. We're just doing a final project. Okay. So hopefully we'll have some fun with this one. And what did I have for the due date? That was the 28th, was it? I think it was the 28th, 6 p.m. for this one, because we're going to present them to each other. And hopefully that'll be a lot of fun. So we'll just say 30 points. Again, the points don't really matter, but it's the points within the category. So if we need to change it, we can. This is our final project. Okay. Come on, Canvas, load for me here. You can do it. I don't know why it's been like super slow. Gotta be I think it's just my CPU is just getting locked down from being too hot or something. We'll see. All right, and then you're going to turn in online a website URL. I'm not going to mark it as a group project. You guys can just both individually submit your URL, and that should be fine. Should be okay there. Okay. All right. Let's see if this works here. Aha! Copy paste. I used this project last year, and I thought it was a lot of fun. Okay. So we're going to make a blackjack game here that we're going to test. Hopefully those links still work. If it doesn't, I can fix it. Maybe I just pop this part out. Yeah, I think I just popped that part out. Okay, there we go. Okay, I think that's good there. So a couple parts to this here then, right? Is that we're making the Blackjack classes so we can play the game and write unit tests to make sure that it works. So we need to build out all the logic, all the classes to play Blackjack. There's a link to the Wikipedia page here. We'll take a look at that in a minute. We're going to run with 6 decks, and you don't reshuffle until you get to 52 cards or less at the end of a hand. So we're going to let players hit, stand, split, and double down. Don't worry about the surrender or insurance nonsense. We don't need to account for that. Then what we're going to do after we play the game is we're going to run 100,000 simulations to figure out a strategy sheet. So based on how often we have a starting hand, we're going to just try one of the actions and record the results. Okay, so how often do we win if my 2 cards that I get are a 5 and an 8? If I have a 5 and an 8, I'm going to try a hit, I'm going to try a stand, I'm going to try I can't split, I could try a double down, and see how often I win. Right? Most of the time you'll lose if you just stand at 13, because that's what's going to happen. So what we're going to see is by running the game 100,000 times, we should get all of our possible 2-card combinations relatively often. Right? There's 13 different face values. We don't actually care about the suits. There's only 13 different face values, but 4 of those 13 are 10 points. The 10, the jack, the queen, and the king are worth 10 points each. Right? So those only really count as 1. So there's really only like 9 different values. You could be a 2, a 3, a 4, a 5, a 6, a 7, 8, 9, or 10, or an ace. Okay, there's 10. Sorry, there's 10 possible faces essentially. So really, in the ways that you can get those in combination, because the order doesn't matter for us, in combination, so 10 combination 2, let's do that math here. 10 C2, 10 choose 2. Why doesn't, okay, that's fine. So Wolfram Alpha will do this for us because it's smart. 10 combination 2. Is that 100? No, 45. That's right. Okay, so only 45 different combinations. That's right, because you can get 9 from the first, 8 of the next, 7, 6, 5. Okay, yeah, I think that's right. Do they have the math for that? Yeah, 10 factorial divided by 2 factorial times 8 factorial. So 10 factorial divided by 8 factorial just gives me 10 times 9. That's 90. Divided by 2 factorial is 2, 45. Look at that. Are you still around, Prof. Peter? Are you impressed with this math? I'm hoping you're still around and you're impressed here. This awesome math. Okay, I was able to tag you. I don't know if that means you're still in chat or not. But this is totally to impress the math profs here. So we're just going to try it. So there's 45 different ways we could get. So we're going to try one with a hit. We're going to try one with a stand. You can't split most of them. I mean, you might not even worry about the double down. I'm not too concerned about trying to double down. So either hit a bunch or stand, right? And see what happens. Right? How often are we losing? How often are we winning? And we're going to see what is the best strategy. So we're going to use that to build out a strategy sheet. So this is like the basic strategy page here. Let's see, can I just link to that? Oh, it opened it. There we go. Yeah. So the basic strategy sheet says, okay, if this is your hand total, this is the action that is most likely to win for you. Okay? I mean, you still lose most of the time because blackjack is a game that favors the house and favors the dealer. So it's not saying that you necessarily have a guaranteed win percentage, but the least losing percentage, if that makes sense. We're going to go for least losing. Okay, so we'll come up with this strategy sheet and say, okay, and we're not doing splits, so don't worry about that. I'm not too concerned. Just look for hits and stands. And these soft totals are when you have an ace. An ace can either be 11 or it can be a 1. So if you have an ace and a 9, your total's 20. That's pretty good. You want to stay. Right? Ace and an 8, sure, you're usually pretty good. Ace and a 7, usually pretty good. Ace and a 6, a lot of times you want to hit more. The DH is for double or hit. So like with ace and a 6, you're almost always hitting, because staying at 17 isn't all that great. You could possibly do better. An ace and a 4 or ace 5, right? So those different soft totals, you almost always hit. Okay, so you'll come up with some sort of odds sheet. Okay, and then we're going to use that strategy sheet to run 100,000 more simulations where we say, okay, given this is the least losing result, let me try that result. So this one here is just random. Just half the time we'll hit, half the time we'll stand, and just record the results. So we're doing a simulation here. We're not doing any math. Right? You could do a lot of math behind the scenes here. What we want to do is figure out, hey, can I make a model in code? And can I run my model a bunch of times to see what my results are? Because there's a lot of things where the math gets really weird sometimes. And being able to build a model and run that model is super helpful. We can kind of test out our theories here. Okay. So we're going to use that strategy sheet to run for 100,000 times, see if we can make some money. Then another part here, we're going to use various strategy sheets, changing a betting, counting cards to find the most effective strategy, simulating each one and adapting the next model. So, hey, was this the best strategy sheet, or what if we just tried this strategy sheet? Can we just plug this in and see which one does better? Right? The thing we come up with our 100,000 tries might be different than this. Is this one going to be any better? And try it. Other things that you can do, you could start counting cards to give you an edge. And if you look here on the Blackjack page, you look at card counting here, it can give you up to a 2% edge over the house if you're properly counting cards. And what that means is we're essentially trying to find out when there's the most 10-point cards in the deck. So as we go through, we start with 6 decks of cards, right? And we know that 4 out of every 13 are worth 10 points. That's almost 25%. Not quite. What is 4 divided by 13? We should check here, right? 4 divided by 13. That, oh, gave me integer division. Thanks, programmer calculator. Okay, 30%. Is that right? 4 out of 13? I thought that was, oh, a third. I kept saying 25%, almost a third. I can't do math. Okay, don't be proud of me anymore, Prof. Peter. So almost a third of your cards. So 30% of your cards or so are 10s. So what you can do is, depending on what value cards you have, if you know how likely it is that there's a 10 going to be coming up next, you will increase your bet. You'll say, okay, because I know there's a lot of 10s left in the deck, I want to bet a lot more money because I'm more likely to get a better hand. Okay? That's what it is. So we can do some sort of variation there to see what we get. So there's a lot of different steps involved, right? A lot of different pieces here. So writing blackjack and writing unit tests just to make sure it works, right? The dealer logic. The dealer will always take cards until they get to 17. Where's the dealer rule here? Where is it here? Here. The dealer here, after all the players have gone, the dealer keeps taking cards until they get to 17 or higher. If they bust, the player wins. If they stop, then whoever has the higher value, the sum of their value of cards wins. Okay? Oh, sorry, I didn't get to the mute button in time. Oh, I tried. Whew. Sorry about that. Okay. So that's our blackjack simulator here. So let me save this. And I'm going to add a rubric to it here. Give me a second. So we got a couple points here for our rubric. Okay, this is the final project. Okay, and this is for grading. There we go. This is blackjack, base game logic. So just getting the game logic in there. Where like you've got the class for blackjack, you can interact with it, you can interact with the player hands, and that sort of thing. I got 6 points here for that. Okay, so a fifth. There we go. A fifth of the project is that initial part. Okay. Then our unit tests for blackjack. Blackjack unit tests, right? So we're testing draw, win, lose, hands against the dealer. Ensure the model works. We run our simulations. Or rounds, right? Rounds. So if my hand is 17 and the dealer's hand is 17, we draw. If my hand is 19 and the dealer's hand is 17, we tie. If my hand is 7 and the dealer busts, I win, right? All these different combinations. Anywhere we have an else, anywhere we have an else, elif block, we need to be testing it, right? So that one's 4 points here. Okay, so the base game and unit tests is a third of the project. Okay, the next one here is doing a 100,000 random hit stand simulations. Generate an odds sheet. Okay, this is coming up with our odds sheet here. Okay, 6 points for that one. So we're just going to try it. So whatever hand we get, we're going to record this was my hand, and I did a hit, and I got this result. I did a stand, and I got this result. And we're just going to run that 100,000 times. Right, so 100,000 divided by 45 or so. What do we get here? That's close to 50 divided by 45. So about 2,200 or so results. Right, so about 1,000 or so we hit, 1,000 or so we stood, and we want to see what the result was from that. You know, what happens when we hit at this number? What happens when we stood at this number? Which one was least likely to lose is our goal there. So we're not always going to have a winning option, but we're going to have a least losing option was the goal there. Okay, 6 points for that one. And then we're going to, using that odds sheet, so using our generated odds sheet from above, try it with 100,000 simulations to generate a baseline win-lose amount. It's probably going to be a loss, right? Because the idea with blackjack is you lose money. Right? That's just how it works here. So 6 points for applying that to it. Okay? Then the last bit, right, the last part here that we're going to do is the part 3. So we're going to try 2 different strategies. Strategies, right, like card counting, bet variance, other odds sheets, and compare with our baseline win-loss amounts. Okay? And that one's 8 points there. That's our 30 points. Okay, so make the game, unit test it, randomize, run 100,000 to see what our odds sheet is. Use that odds sheet to figure out how much we win or lost with that. What is the least losing that we can figure out with our odds sheet, and then let's try some other methods, whether or not we're card counting, doing a bet variance, whatever other odds we want to try and figure out here. So usually like card counting and bet variance kind of go hand in hand. You bet more when the odds are in your favor, when the count is in your favor and there's more tens in the deck, and you bet less when there's less. That's all. Usually that sort of thing will get you kicked out at the casino. Interestingly, Wikipedia claims, and I don't know if this is actually true or not, but card counting is legal as long as you're not using an external device, but if a casino realizes you're counting, it might kick you out, because it gives you an advantage against them. And they're not in the business of giving away money, believe it or not. Big newsflash there. Casinos are not in the business of giving away money. They're in the business of taking people's money. Okay? That's sort of how that works. Okay? Thoughts, questions, comments, concerns on our final project here? And you're welcome to do this in pairs. Create the rubric. Okay? So, initial part 2, part 3. And we got a month to do this one here. Okay, so it's kind of a big project, but it should hopefully be interesting to run, create a model, run some simulations, try some different strategies, and see what kind of results we can get back out. We're not really doing anything super fancy with any data science libraries, but we're just kind of doing this sort of modeling, testing by hand. Right? Then when you learn all the cool data science libraries, you can appreciate how much easier they are to use. Is that fair? Is that okay to say? Hopefully that makes sense. Okay. And again, it's the math behind this honestly is a little funky, like to figure out actual odds and that sort of thing. And this one's kind of fun. So I like this Blackjack project. I think it's very interesting here. Okay. How do we feel so far? Grenjith laughs. Okay, sure. Yeah, if you want to partner up, I definitely would encourage that. That's great. I can get you set up with a shared GitHub repository if you want, or you can make your own. Just make sure I have access to it so I can grade it when you go turn it in when you're done. Okay, and do make sure it's private, would you? If you need any help with that, I can definitely point you in the right direction there. Okay. Oh yeah, the comment about casinos. Believe it or not, they don't want to give away money. They do occasionally. It's good for business, actually. That's one of the reasons why the lottery law in Michigan currently says if you want to claim a winning ticket, you need to reveal your identity. You're not allowed to claim it anonymously because they want to be able to prove that real people occasionally win money and it's not just a giant Ponzi scheme. I mean, which it's not. It's just a poor tax. It's a tax on people who can least afford it. Rich people don't play the lottery. It's just sort of a fact there. Okay. But there's all sorts of things about that. So, sure, why not? All right, Wolfram Alpha, we're all set here. Excuse me. All right, so I think we're good here. We got the final project. We're running low on time, and we got a little bit more about binary search trees. It's probably going to take more than 20 minutes to talk about. So why don't we save that for next week, and we'll just bump a little bit of that sorting and selection stuff out to next week, and we can go from there. Okay, we can call it a little bit early today. Get to work on the Polynomial Project if you're not done yet. Maybe start thinking about this final project. We can go from there. You know what? Actually, how many people are even in the course at the moment? If we want to do this in groups of 3 even, I might be open to doing this in groups of 3. Oh, the lab? Yeah, building out our hash map, right? Yeah, we could work on that. Lab 8 was the hash maps, right? Let me go find that one. Yeah, let's see. Oh, I didn't even give it a name. I just called it lab 8. All right, yeah, our basic hash map, right? Kind of using that bucket at each location here. Okay, and again, we're not going to do this like super well. We don't need to do the find the next prime number value so that we mod things. It works out really nice. It's okay to we'll just do an even number, and again, the distribution, it won't be perfectly uniform, but we won't be too sad about that. We call ours a hash map. Right, let me zoom this in a little bit here. So there's a lot of cool functions we use with hash maps dealing with keys and values and those sorts of things here. So let's do the init method here. That just creates a hash map, right? So we need a our storage here, right, is a list. Okay. What we're going to put there is we're going to have like this internal node. This is that bucket idea, right? Where we're just going to put things in this bucket here. And so the node has an init, it takes a self, it takes the data, or I don't know, the value maybe, we'll call it a value, the thing that it's storing, and then it has self value as the value, and self next is none to start with. So we're just going to do a singly linked item here to see if each item matches. So like when we hash the value, we mod it by the size of our data storage to find out which spot we're going to put it in, and we drop it in that bucket. And the bucket will create a bunch of nodes, right? Each bucket is a node, and if it's empty, sure, we drop it in on top. If there's something there, we check, does it have the same value or not? If it doesn't have the same value, look at the next link, look at the next link, look at the next link, on and on and on down. This sort of idea. Okay, so we'll make data. That's all good there. We need to size it then. So we're going to say it equals that times, what was it, 10 times none? I forget what it was. Or we can just throw a bunch in here. That's fine. I'll say for index is 0. I'm sorry. For index in range 10. We'll say self.data.append. We'll append just a none. We'll put nothing in there. Okay? That way, but I'll have 10 spots to put things in. Okay? And then we can add an item. Give it an item. Again, you could do all this with a map. We're just going to take it easy for right now for this example because we're a little short on time. We'll do individual items instead of a map. All you do is you would take a key and an optional value and you would turn it into the key value pair. That's perfectly fine. So we're going to do the item. Okay, and we need to get the hash of the item. So the item hash is equal to item.hash, hash of the item. Okay, and then the item index. Oh, that's just a reminder email or phone call. That's fine. So the index is going to be my item hash modulus the length of self data. Right? If I have 10 slots, take the hash, figure out which one of those 10 slots it falls into. Okay? Then I need to check. Now this is actually trying to put it in the bucket. We're going to say if my self.data at the item index is none, great, that means it's empty, I can put it in. So I'll say, great, let's make a new one here. Equals a node given the item. Let's make a new node, self.node, put it in there. Right? If it was empty, sure, now I've got that. If it wasn't empty, this is my else case here. Right? I need to start checking to see if it already existed. And again, with a real map, right? If the keys match, you just update the value. In our case, if they're the same, there's nothing really to do there for us because we're just saying, here's the key. Should we do an okay? Well, fine. We'll do a key and a value. Feeling bad now. And we always hash off of the key. So that takes a key and a value. Dot key equals the key. Sure. New node of key and value. And value can default to none if we don't give it another item here. Okay. There, now I'm feeling a little better. Okay, so if it's not none, we need to check. So we need to have a current node equals the node here. And then now we need to start checking. So we're really just looping while current node does not equal none, right? Or is not none, right? Is not none. I think is more proper. Okay, stop yelling here. So if it's not none, let's check. Let's see if current node dot key is equal to my key. Right? This is, we're actually checking equality here. And this is why when we need an item to be hashable, it has to have a hash function and it has to have an equality function. Okay, and it needs to be a decent hash function so you get good distribution. Again, this uniform distribution, pie in the sky goal, great, all well and good. There's cool math around that you can worry about later. And then we need to check, does it equal another value? Okay, so if the key equals the key, then we're going to set the current node dot value to the value you gave me. So if we found a matching key, we update it. If it's not, then current node moves to next. Current node dot next. Nope. Current node next. Okay, so if we didn't find a match, just go to the next one. If it's not none, go to the next one. If it is none here, then so really at this point, then we can just return. Right, we're done. If we get through the loop and we found one that current node is none, well, we can't add one where current node is none. We've gone too far. Right, with the linked lists, because we're not doubly linked, we can only ever set the next. So what we actually want to do, we want to say, well, current node dot next is not none. We want to do this thing. Right? So as long as my next is not none, I want to keep on checking. I want to keep on checking here. So this gets to be a little funny. So we're going to check if the next key, and then we'll set the next value. Okay, so I need to check the current one first. So I'm going to check if current node dot key is equal to the key, then current node value equals the value. And if that didn't happen, then I want to start checking all these next things, right? Because I need to check the first one if it exists, because I can only ever set next. So if I finish this loop, if next is none, right, my while loop is done, then I'm going to set current nodes next equal to a node given the key and the value. Right, I'm going to add a term, self.node, right? So we need to check and see, okay, let me go look. I checked the first one, and I'm going to see, hey, if you have a next. If you don't have a next, sure, next it becomes this, because you didn't match. You weren't the same key. If you do have a next, check, is the next the key? If it is, set the value, done. If it's not, walk to the next one. Right, this return makes sure that we don't accidentally set the next one by mistake. So as soon as we find a matching key, set it, we're done. Or if we don't find one, you become the last value here. But we need to check every single other one in the list there. Okay? That adds a shared item. I don't know if you want to call it that. That's fine. And then we'll do a get. Find get item out given a key. Right? We need to get the hash, get the index. And then if it's none, sure. Raise a key error, right? So if there was nothing there, obviously we don't have it. That's a bad key. Okay, otherwise, now let's get the current node equals here. Okay, and this one we can keep on looping here. So now we can say while current node is not none, if current node.key equals the key, return the value. If we didn't do that, I'm sorry, current node value. If we didn't do that, then current node becomes current node's next. Right? If we get all the way through the loop and we haven't returned, we're going to raise a key error. Right? Just keep on looping until we find not none. Keep on checking. If we found the key, return the value. If we found the key, return the value. If we get all the way to the end because the loop stopped and we didn't return a key, we don't have that key. That's a key error. Right? Dictionaries yell at us. We try and get an item out by key that doesn't exist. Okay? We can add, we can get. The other thing we need to do, right, is we need to be able to resize. We need to track the number of items that we have here. So we need to store the self.number of items. Number of items, right, starts off at 0, and every time we go add something, we're going to add 1. Right, we'll go add 1 to it. Then we need to check and see about resizing. Right, if self dot, I don't know, or I don't know what we want to call it. Say self dot check for resize. Sure. And we'll add a method here. So we'll define a little helper method. Check for resize. Okay. So we need some sort of our load trigger, our threshold. What do we call that? There was a term for it. I'm forgetting right now. The fill rate or fill value or something. So we'll have like a max fill equals, I don't know, somewhere around like 0.75. Sure, why not? Okay, so we'll say if self.number of items divided by the length of self.data is greater than the self.maxfill, right? If we have more than 75% full, right, then we need to resize. Okay, that's our check. We need to resize. Well, to resize, what we need to do is we need to create a new storage. We need to rehash everything, put it into new buckets here with the new data storage. Right, it's kind of a big pain actually to do all this, you know, for every single item there, but it's doable. It's okay. So what we're going to do is we're going to say we're going to have old data equals self data. Okay, we're going to store that. Boom, we got it. Okay, then we're going to change data. Self data equals a new list, right, of none. Was it just none times something? I think it was none times that. That sounds right. Equals none times 10. I think that's what it was. We don't have to do any of that nonsense. And what size do we want? Well, we want the length of self data times 2. Double size it, just double. Again, doing a geometric doubling. Not perfect. We should do some sort of prime number thing to get better distribution, but that's fine for now. Thing with prime values for better distribution, but we aren't. Okay, we're not going to do that. Okay, we can take that up another time. Can we do a basic one? Right, we can worry about those optimizations later. So make a new self data storage. Okay, cool. Then what we want to do is we need to put all of the old data back into the new data. Well, we have a way that we can add items here, right? Which is really cool. So we're going to say for node in old data, right? So if node is not none, then we can go do it, right? We need to get that key and value out. So we're going to have a current node equals node. And while current node, oh, actually we can do that, right? So we'll do that right off the bat. We'll say current node equals the node. And while current node is not none, because maybe it is none right off the bat, right? If it's not none, we need to go and grab that key and value. We'll call self.addItem, given the current node key and the current node value, right? Just go rehash, right? Re-add it to the new data storage. We've reassigned self data, so we have new storage. Add will just go add it back for us. Right, and then current node equals current node's next. Right, this is going to rehash every single item, rekey it, rehash it, remod it, put it right back in the right location here. Okay, it's going to add it all. Add them all back for us. That's it. So if we resize, right, we need to create new storage and then rehash everything that we have stored. Again, because they're all this singly linked list, they're all these buckets here, right? It might be none because I might not have put anything there ever. I might have had a bunch of things in like 3 different buckets out of my 10. I don't know. If it's not none, I've got something. Let's add it and let's get the next one. If it's not none, add the next one. Hey, Uncle Bill, thanks for dropping on by. Okay, so we can get values, we can add items, we can get items out. That's pretty good. Deleting items is obnoxious. It's not too terribly bad. We just have to do the skipping over thing. So we can add that. So we'll say define delete item given a key here. Again, do this sort of thing here. And it's very similar. First hash it. If it's not there, bad things happen. Otherwise, we have a current node. Okay. As long as it's not none, if the key matches, we're not returning the value. What we need to do is we need to skip it. Right? Well, the problem is I can't skip something where I already am, so I need to be looking at the next now. Because the only thing we do, remember the singly linked list, the only thing you can do is jump an item. Okay? So we need to be looking at the next value here. We're going to say if my current node dot key is equal to the key, well then what I need to do is I'm going to take the value is my current node dot value, and then I'm going to set, move the bucket, right? We're going to jump that one as the current node's next. So if the first item matches, great, take the value and then move the bucket, right? Jump over it in the bucket here. And then we can return the value. Usually you return the value when you're done. If we didn't do that, right, as long as I have a next now, we want to keep on moving. If I don't have a next, right, automatically we're done because it wasn't the first thing, and if I don't have a next, I raised a key error. No good. We're going to check, hey, if the next key matches the key, great, we'll have the value is the current node's next value, and then we'll take current node's next equals the current node's next. I know next is not none, so it exists. So it's next, whatever it happens to be, will be next, and we can return value. If it's not, then walk, move to the next one. Right? Sometimes this is helpful to whiteboard. So let's throw this out here. Let's clear this one off, and let's imagine this. So imagine our storage here, and let's just do a bunch of integers, right? So we got a bunch of digits here. So like we had like, maybe this is 12 and 32 and 52, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure. Okay. So we've got room for 10, and we're going to throw a bunch of numbers in here. So let's say we want to remove 32. So we're going to look here. It's not this one. Is it that next one? Yes, it is. Remember, this is a node here with a next. This is a node with a next. This is a node. Its next is none. Doesn't exist. Okay? So in order to delete something, we need to be before it and jump over it. So we need to change our next to be the next. Okay? If it was the first one, we just say, hey, the bucket doesn't start here. The bucket starts here. That's all. Okay? Hopefully drawing that picture helps a little bit. Okay? You guys feeling okay so far? And again, we would do an iterator sort of thing. Being able to iterate is really similar to this resize loop here. We take the data. Where's my resize? Here. Go through every node. If it's not none, yield the item. Move on to the next one. Right? So to iterate through, we're just going to go, and this is why there's no guaranteed ordering in dictionaries, because we don't know what that internal storage looks like. We don't know how they put them in and what bucket we're going to hit first. We don't know. So there's no order guarantee when we iterate over these. So we can add an iterator. We're about out of time here. So hopefully this got you far for the lab. I think adding the iterator is probably the last thing we need to do there. We can iterate over it. And you can probably use the proper method names. I don't think it's get and it's not add. There's other method names that I'd have to go look at the textbook because I don't remember those ever off the top of my head. But hopefully that's making sense. Does that feel okay, folks? That's what we did for the lab there. Oops, 2001. There we go. I can do that. All right, so this is lab 8. Mostly done. And sorry, I didn't follow off the text exactly well there, but that's the gist of our hash map. And again, when we delete items, eventually we could resize downward if we wanted to. And that is an option to resize downward. This is only resizing up. But again, those are other little optimizations that we can worry about later. We're just trying to get into the basics of the data structure, what it looks like. What page in the text? Good question. Let me go open that up here real quick. I do have a hard copy somewhere, but I think it's actually on campus. And I'm finally actually allowed back on campus, but like I have to register and say, hey, I need to go to campus for a particular reason. So I've not been on campus for more than a year now, which is a little weird feeling, to be honest. It's I don't know. I don't want to say like this remote thing feels normal, but kind of getting there, and like this idea of going back to campus feels kind of funny. So let's see our hash table. So page 422 is the start of the hash table implementation in the text. 422. Let's see. Yeah, 422. So again, he uses the base thing, and he has all sorts of really cool things, the prime values and capacities, really good stuff. But again, we don't need to worry too much about any of those extra fancy things. Yeah, so a set item and get item. That's right, for keys and values, and delete items. There we go. Look at it. I can fix it real quick then, right? So add item is, this is a set item. Takes a key and a value. Cool, 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 cool. And the get item is under get item, given a key. Oops, sorry, get item. Get item. Look at that. I can follow along. Delete item. Delete item. Given a key. Okay. Looks like his load factor. Oh, load factor. There we go. Max fill. Load factor. That's fine. You get max fill. I don't know. Okay, we'll refactor rename. Refactor rename. This is load factor. There we go. He was using 0.5, it looks like, with resizing. So sure, why not? Oh, C times none. That's fine. I think this works. We could try it and see. Okay. And we use the separate chaining. And so he has different implementations of it. So we were doing ours with our bucket here. Okay. Don't worry about the linear probing. We don't want to follow any of that. All right. Cool. So let's fixed up some terms. Function names. Hit and push. All right. Page 422 or so. All right. Awesome. If you guys don't have anything else, we'll call it a day. Let's see who else we can pester in Twitch land. See if anyone else is around doing anything fun. Ooh, Dr. Mick is online. We got to go hang out with Dr. Mick. That was super cool. And he's playing Skyrim, which is like the best game ever. So we'll go hang out there with him. Folks, enjoy. He is amazing. Great mental health information. You guys fabulous. You folks take care. I'll see you on Monday for lab.